Hello, students. I wanted to take the opportunity to do a couple more examples of sketching polynomials. We covered some of these ideas last week, but you have another section in your book that just focuses on sketching polynomials, not necessarily using transformations. So I wanted to just do a couple of examples where we review roots, multiplicities, and also end behavior. So let me go ahead and share my screen. Now, later on in the course, we will learn some new theorems that will allow us to compute rational zeros when we can't use standard factoring techniques. And so when we get to that, we will cover that theorem and apprise you of how we can work with different situations when we have integer polynomials like we have here. But notice what we want to do is utilize the zeros and their multiplicities and then consider some end behavior. Now, first off, we notice that the two factors here in this polynomial can be broken down further. So let's go ahead and do that. So we can factor an x in the first factor. And then, of course, here by the AC method, we've got -6, that is AC equals -6. And of course, we could write that as a -3 times a 2, and that'll give us the middle term. So we have x minus 3, x plus 2. Now, when you look at this, you're thinking, okay, well, we've got some multiplicities going on here. So we have, if you like, x to the first power. I won't write that. And then we'll have x minus 3 squared, and then x plus 2. So we have a complete factorization of the polynomial. So let's go ahead and write this for our zeros. We have the 0, 0 of multiplicity 1. We have the 0, 3 of multiplicity 2. And then we have the 0, -2 of multiplicity 1. Now, remember, the multiplicities give us the behavior at the x-axis. So here, this will correspond to cross the x-axis. The even multiplicity will be touch. And then, of course, at -2, we cross again, since we have the odd multiplicity. So again, obviously, if you can determine a number of real zeros of a polynomial, that's going to be a great assistance in sketching it until we learn some other techniques from the calculus. But we will always take advantage of the zeros, especially the real zeros of a polynomial. So now we can sketch our number line to do a sign test or sign analysis. And we'll go ahead and write in our zeros. So we have a -2, we have a 0, and we have a 3. So what we can do at this point is just, again, very, very simply, let's just think of substituting a very large number greater than 3, like 100. So when we look at that, we see the dominating terms here, x squared, x squared. This is going to give us a positive output because the other terms will be small relative to the squared terms. So we're positive greater than 3. But notice at 3, we touch. So we positive, and then we touch. We're still positive. As we approach 0, we must cross. And then, of course, we must cross at -2. So this technique simply, this is not a graph of the function. This is just simply a line indicating above or below. So we have plus, above. We still have plus, above. And then we have negative. The values of the polynomial are negative in this interval. So we have below. And then we have plus, above. Now, one thing that's nice about this sign analysis is that it automatically gives you in this particular case, the end behavior. But notice if you wanted to do that separately, we can easily see that the leading term will just be the product of the two x squared terms. So we have a leading term of x to the fourth. And then, of course, we're good. So if we did the limit as x approaches infinity of our polynomial, that will just be the sine of x to the fourth attached to infinity. And of course, x is positive. So this gives us positive infinity, since x to the fourth would give us a positive number. Again, we see that to be the case right here. As x gets arbitrarily large, the values of the polynomial become larger. And of course, the limit as x approaches negative infinity of p of x will just be the sine of x to the fourth attached to infinity. And of course, here x is less than 0. But of course, if we raise a number less than 0 to the even power of 4, the negative absorbs. So we still get infinity, which we see from the sign analysis. So again, the understanding the multiplicities allows for a very quick sign test, as long as you establish one correctly. Establish one at one of the extremes, and then you're good. So you can always just simply apply some large number and then look at the largest terms in each of the factors, taking into account any negative coefficients. And that would be a very simple way to get this process done. So now just as some additional ideas here, we know from our last lecture that the zeros are very useful. And also we can look for a y-intercept, P of 0. P of 0 is really simple in this case. In one of the problems we did last week, that we got a really large y-intercept just because of the nature of the polynomial that I made up. So this one's a little bit simpler. But notice now, if you just replace x with 0, here we get a -6. And of course, this whole term is 0. So this just gives us 0 times a -6, which is clearly 0. So again, the x-intercept and the y-intercept are the same. So we say y-intercept of 0. So now we can just do a simple sketch. Again, we don't have increasing, decreasing, and we don't have the concavity that we will learn about in the calculus. But that's fine. We can still get a reasonable graph. So let's go ahead and mark off our zeros. -2, and then we have the 0, 0, and then of course 3. So we have -2, 0, and we have the 3 here. And I'll put a little to the side. I guess that's a little. Let me just go ahead and draw it. Then I'll put in the number, so we don't just end up running over it. That might be a little bit easier to do. Notice now, of course, this is a fourth degree. I like to do the fourth degree because they have really, the even degrees have the interesting outputs that you don't always expect. So we're above, and then we have to cross, and then go below. So let's do this. So cross, and then of course we have to ease in and come right back up. Something like that, nice and smooth. Then my graph doesn't look very smooth. It's nice and smooth. So this would be a graph of P of X. And let me just smooth that out just a little bit. There we go. It's nice and smooth. Polynomials are very nice curves. They're differentiable curves. So they're nice and smooth. No corners, no cusps. Just really nice, very nice continuous curve. So that just gives you a reasonable picture. Now, what do we have in store for us when we get to the calculus? Well, we know the extreme values are fine, but we'll be able to determine how low this goes. That is, determine a local or a relative minimum, and also here a local or a relative maximum. that we would look at these as being places of horizontal tangency. So we think of horizontal tangents here, horizontal tangent here, and a horizontal tangent here. Now that structure we will learn when we get to the calculus. And so we will also be able to refine the graph in terms of its shape. You know, it looks like we've got an upward concavity, then we're frowning, a downward concavity, then upward. And we can infer some of that just by the nature of the zeros. But that's what we will be able to do when we get to the calculus to get the most precise graph. But for now, this is more than sufficient. Now let's try one more. Again, I just want to give you the basic construct of graphing a polynomial using zeros in behavior, multiplicities, intercepts. Very straightforward. So here's another example. It's also degree 4, but I think it's interesting. So we have P of x equals negative 2x to the 4th minus x squared plus a 3. Now, I threw in some negatives here just so we get some practice with some of the negatives. And also, I've set this up so that we actually can factor it. So the first thing I'm going to do is factor the negative. This gives us a 2x to the 4th plus x squared minus 3. Now, this makes it a little bit easier to deal with when you have a leading coefficient that's positive. We still have the negative here, which we must address with the signs. So that's very important. But notice with the AC, we have 2 times the negative 3. And of course, to retain the plus term in front of the x squared, this being in quadratic form, we'll just move the negative with the 2. So we have negative 2 times the 3, and that sum giving us the 1. So notice we see that our polynomial has quadratic form, a very important form that you used on your first test. Quadratic form is very useful. We depend on the theory of the quadratic equation. It occurs in all places in mathematics. They say it's ubiquitous. That means we see it in mathematics, the sciences, engineering. Very, very useful theory of the quadratic function. So now we can factor. So we've got, in this case, we've got our negative. So we've got 2x to the 4th minus 2x squared plus 3x squared minus 3. So we'll factor by grouping. So we have a 2x squared, and we have an x squared minus 1, and we have plus 3 times x squared minus 1. Now, of course, that'll give us the additive inverse, and then, of course, we have the 2x squared plus the 3, and we have the x squared minus 1. Just by the distributive law, the x squared minus 1 multiplies the 2x squared and also the 3, and so we get this. Now, what we notice is that we can continue to factor the difference of 2 squares here, but we notice that this does have zeros, but they're not real. Let's just go ahead and factor them just to get some practice. So we have a negative 2, and we have x squared plus 3 halves. And then, of course, we get x minus 1 times x plus 1. So this gives us a factorization. And since we've worked with imaginary zeros, we can factor this with the imaginary unit. Just to note that, even though this is not going to show up in our graph, so we'll have x minus the square root of 3 halves I, and x plus the square root of 3 halves I, and then, of course, x minus 1 and x plus 1. But what I want to show you here is that these will be the only zeros that we will use, these simply being imaginary, but just giving us practice with working with imaginary zeros. And then you're going to also notice here that with the the even powers, we have what we call an even function. So I'll just say observe The domain in this case is all reals. We haven't restricted it. So the domain of P is all reals, our properties of functions. And also notice P of negative x, or the additive inverse of x, is negative 2 negative x to the fourth minus negative x squared plus a 3. And of course, the even powers absorb the negatives. So we get the negative of 2x to the fourth minus x squared plus a 3. And this is absolutely P of x. So if we replace x with its additive inverse, we do not change the function. And so by definition, P is even. I just wanted to add an example that goes back to that. We did some really interesting examples with even and odd functions, and it's good to go back and review. So now we expect that the graph will have y-axis symmetry. That is y-axis symmetry for the graph. All right. And again, the imaginary zeros, they're not going to interact with the graph in a tangible way because we're doing a real axis graph. So let's go ahead and get a nice example of this. And I want to go ahead and draw this, but I'm going to do the sign chart just right here. There's our graph. It's going to be easy to do. But we just have our -1 and our 1. So we've got, I'll write this over here, zeros. We have 1 of multiplicity 1, and we have -1 of multiplicity 1. So here, -1 and 1. And then, of course, P of 0, we can go to the original function, is just 3. So that is our y-intercept is 3. So very basic information that we can get from that, and we're glad for it. So now notice that this is where we can interact with the leading term, and we can just look here. Looking at the most factored form is probably a little bit more difficult, but if we focus on the leading term here and just replace x with a very, very large number, notice the overall sign will be dominated by the negative here. So that will give us a negative output. So again, we have negative, and then we cross, and then we cross again because these have odd multiplicities. So we have negative below. The multiplicities are very useful. We have positive above, and we have negative below. So we've got our y-intercept, a little bit easier to draw. We'll go ahead and spread things out. So we've got the 3, and I'll spread out the 1 and the -1 a little bit. And so we'll have a function that looks somewhat parabolic just because there's not really much else it can do. Now, what's interesting about this particular function is that because of these negative coefficients, that's the largest value. We're kind of forced to do that just with the arithmetic. So this would be a very reasonable sketch of P that's not too bad. So here's our P of x. Again, with the negatives here, the values that we put in or substitute for x other than 0 will always make this value less than 3. So we get a very simple maximum without any calculus. So again, ladies and gentlemen, just remember at this point, what we're trying to focus on are the real zeros, their multiplicities, so we know the interaction of the graph with the x-axis, the end behavior, which again we can get with the sign convention using the multiplicities, and then any intercepts. Again, as we get to the calculus, we will find other means to make the graph much more precise, but we still can get quite a bit of information doing what we're doing now with these strategies. So like I said before, I just wanted to do a couple more examples of this. I think this is something that you will find is very straightforward and something that will be very useful as you continue through this course and also into the calculus sequence. So we're done with this, and I'll see you later for rational functions.